Alright, this time around we're going to take a look at what gravitational fields are, which is what we actually have a picture of. And so gravitational fields build directly off of gravity. So hopefully you have a pretty good understanding of gravity, and if you don't, go back and watch that other video previous to this one. So first we're just going to talk about a quick review. Okay, so the distance between two objects and what its effect is on gravitational force. So remember, gravitational forces are attractive. So between the Earth and the Moon here, we have some gravitational forces. Okay, if the Earth and the Moon were to be farther apart, then those gravitational forces would be less attractive. Okay, our forces wouldn't be as strong, and then our orbit for the Moon would be a lot bigger. And so it might be something like this if it were out at that distance, whereas here they'd be closer. Okay, our gravitational forces would be stronger at a closer distance. Okay, the second thing that we looked at, okay, was looking at the mass of the objects. Okay, so for example, in this situation, let's say our gravitational force between the two objects would be like this. Okay, well, if we were to increase the mass of an object, like let's say we had a bigger planet, like Jupiter, of course, is bigger than Earth. Well, what if the Earth was bigger? Well, if the Earth was bigger, it would have a greater gravitational force. So maybe our gravitational forces would be more attractive like this. Okay, so it would be able to hang on to its moon a lot tighter, and its orbit then would be a lot closer than what it was when the Earth was smaller or for a smaller planet. Okay, and so the opposite, of course, is also true. If you got a smaller planet, then the gravitational force would be less. Okay, and we could also look at the gravitational force of the Moon. Okay, so if the Moon was bigger, the same thing would happen. We'd have a bigger gravitational force. Okay, if the Moon was smaller, there'd be less of a gravitational force between the objects. Okay, and then don't forget that small objects too have a gravitational force between them. They're just considered negligible because of the size of these objects. So there is a gravitational attraction between our toys here of Lois and Superman. Okay, and it still follows the same rule. If they're closer together, okay, then of course our gravitational forces would be bigger. Okay, if they're farther apart, then our gravitational forces would be smaller. Okay, and so we'd have something more like that. And if we have bigger objects, okay, then our gravitational forces again would be much bigger as well. Okay, so these gravitational forces then keeps together our solar systems. Okay, very large scale systems here, like Jupiter obviously is able to go around the sun because of those gravitational forces. The same with Saturn. It orbits around the sun as well because of the gravitational forces between the sun and Saturn. Okay, so that's going to be true for all of these different items here. And finally, we can notice here in the center, this is really just a galaxy. Okay, at the center of a galaxy is a huge, dense mass of different material. Okay, that's the densest part of the most massive section of a galaxy. So there's many, many millions and billions of stars there. Okay, and as you get farther and farther out here, toward the edges, these tails, well, they're not as dense. Okay, so our less massive objects are out here. So it's kind of like a giant solar system in a way. So there is, again, gravitational attraction between these different areas. So even a galaxy is able to stay together because of these gravitational attractive forces. All right, so now let's take a look at something new. So this, you need to make sure you add to your journal. So this is what a gravitational field is. Okay, gravitational fields show the gravity force vectors. Okay, and you can see then that they're pointing to the center of that object. So if I were to continue on with each one of these force vectors, here's the center of my Earth here, every single one of these force vectors would be pointing directly to the Earth's very center. Okay, so if you had a hole through the Earth, for example, like a cave or something like that, or a canyon, okay, going down a little ways, of course you're going to fall into it and you'd be falling towards the center of Earth. Okay. Now the other thing that you'll probably notice are these little red lines, circular lines going out and above Earth. Okay, these are the gravitational field lines. Okay, so as you go farther away, you're noticing that the distance between these gravitational field lines are increasing each time. And that's because the strength of gravity, as you get farther and farther away, is going to get less and less and less. So these distances here are getting less and less and less as we get closer to Earth's surface, meaning here the gravitational field is really strong near the surface of Earth. Well, up here in the atmosphere, it's going to be much less. Okay? And so that's how gravitational fields work. The farther the distance equals field lines that are farther apart, meaning we get weaker gravitational fields. Now that's going to happen in the atmosphere. So these are the different layers of the atmosphere. Okay, so we'll move this over so you can read it, but we got the troposphere, stratosphere, mesosphere, thermosphere. So these are our different layers of the atmosphere. Well, as we go up into the atmosphere, of course, our gravitational field lines are going to get weaker and weaker. So I'm just going to kind of draw them in here. So here's a gravitational field line, and then maybe the next one's a little bit farther apart. Next one's a little bit farther apart, a little bit farther apart, and so on. Okay, so those are our gravitational field lines. Well, the distances between each one of these gravitational field lines tells us how strong they are. Okay, so the greater that distance, the weaker they are. Okay, so if I were to have, let's say, Superman takes off and he starts flying here and he stops right there, well, there's less gravity pushing down on him at this spot in the mesosphere than there is here in the troposphere. So it's actually harder for him to fly in the troposphere and easier for him to fly in the mesosphere because there's less gravity up here. Okay, so at some point you can escape the ability to fall. So if this was a normal person, of course, they'd be falling, right? Okay, well, at some point we'll be high enough where those gravitational field lines don't pull on us hard enough and we just go into orbit. And so he'd be orbiting along here and around the planet. Okay, if you're closer to the surface, the gravitational field lines like here would cause Superman, if you weren't flying, to just fall. Okay, so that's how gravitational field lines really work. The farther away you are from the Earth's surface, the less the gravitational field is going to affect you. Okay, so let's say I take the weight, for example, of Superman here versus here. Okay, well, there's less gravity in the mesosphere, there's going to be less weight. Okay, more gravity in the troposphere, more weight. Well, the sun, of course, has gravitational field lines as well. So, again, the closer you are to the sun, okay, the closer or greater or stronger those gravitational field lines are going to be. And as you go farther and farther and farther away, those gravitational field lines are going to get farther apart, meaning they're going to be weaker. Okay, so at some point here, you're going to be super close. Well, if you're too close, it's just going to draw you right in. Okay, whereas if, like with the Earth situation, we're in the gravitational field, of course, of the sun, but we're pretty far away. So we're not going to fall. We're not going to go this way. Instead, we're going to orbit around. So that's the difference between falling into it versus orbiting. It depends on where you are compared to those gravitational field lines. Okay, and remember, even with the sun, all the gravitational pull is going to be going right to the center. Okay, so larger massed objects are going to have greater gravitational fields. Well, the Earth, of course, is bigger than the Moon. So here's the gravitational field of the Earth. And it just gets farther and farther away from itself each time. Well, the moon, of course, is much smaller. So its gravitational field is going to be a lot weaker. Okay, so how that might affect our particular, so our rocket here is out here flying along. Well, if it's in a gravitational field and it turns off its engines here, it'll probably just go into orbit around the Earth. Okay, and so it'll stay in orbit. And then you got to turn its engine on, it's got to escape that. Okay, so you got to put some energy into it to escape that orbit. Well, as it gets closer to the moon, well, these are weaker gravitational fields. So even though it's about the same distance over here, okay, because the moon is smaller, its pull on our rocket here is going to be less. So we're going to be able to escape into deeper space a lot easier than we would with the Earth. So in blue we have these gravitational force vectors, okay, and this again pointing to the center of Earth. Okay, so we're going to draw in these gravitational fields. Okay, so the closer you are to the surface, remember the closer together these field lines are going to be. Okay, and then we have another one that's a little bit farther apart, and the next one is going to be even farther apart. Okay. Now again, we can't see gravitational fields, but we can feel them and we can measure them. Okay. Now, if we were to take Superman, he flies up into the... So Superman starts flying up into the atmosphere here. Well, in this gravitational field way up here, there's going to be less gravitational pull on him. Okay, these field lines are farther apart. So it's weaker up here. Okay, as he moves down in this layer, it's a little bit stronger field. Those forces are closer together, and it's going to pull him down to Earth a little bit easier. And so as he gets closer and closer to Earth, well, way down here, the gravitational field lines are really close together, so it's going to pull on him even more so. So we have stronger field lines near the surface, weaker field lines above. Okay. All right, in this last slide, we can see a bunch of different ways to draw the gravitational field lines. In the top left, then, we have the one that we've been really kind of using in that first slide. You can see it's been kind of drawn in for us. And then these arrows get farther and farther apart the farther you go. In this one here, you got to kind of imagine it, but for the most part, you can also kind of see the distance between my arrows here is getting greater. As we get closer to the Earth, the distance between my arrows is getting closer together. And so that's another way of doing your gravitational field lines. Okay, you can also see here's another way that we could do a gravitational field line. Okay, and as we go farther and farther away from our black hole, for example, these field lines get farther and farther apart, meaning the force from that black hole gets less and less and less the farther away you go. And over here we have another way of drawing it. Okay, our field lines farther apart, less gravitational force. Field lines closer together here, more. Okay, and then finally, this is the one that we were also looking at a little bit earlier as well. The higher up in the atmosphere we go, those gravitational forces get less and less and less. But remember, you really got to talk about big distances for those gravitational field lines to really have an effect. Okay, for the most part, it's always going to be 9.8 newtons on Earth. You got to be pretty far into the atmosphere for it to be anything that you could really measure and feel as being a big difference.